So today we get to start our second half of Chapter 5. And Chapter 5 is all about inverses. And then now we're going to spice it up a little bit. We're going to look at these inverses of exponential functions. So we're actually going to explore some exponential functions and look at those exponential functions. See if we can come up with a pattern to be able to use when it comes to our inverses. All right, so we've been looking at inverses for this whole chapter, and we've played around with different families of functions. We've looked at linear functions, we've looked at linear functions and quadratic functions. We really haven't touched like the inverses of absolute values. That's later down the road. But now we get to look at exponential functions. Sound good? So, everybody remember what an exponential function looks like? Maybe, sorta, right? Yeah. So if we had some function and we write it like as b to the x, ooh, that blue is not very good looking up there, is it? Let's try green, see if that works a little bit better. So y equals b to the x. So we started exponential functions. We talked about them even last semester, and we always knew we were looking at an exponential function because our exponent, or our power, was a variable, right? And a lot of times you talk about either like exponential growth or exponential decay when it comes to exponential functions. Oh, let me mark this attendance. All right. All right, got them into the meeting. Right. So that's the one that we have to find the inverse of that good guy. And like ultimately we know that we have to, if we wanted to find the inverse, we're switching the x's and y's. Right, so if I switch the x's and y's, now I have this looking thing. And then after I switch the x's and y's, what do I need to do? Solve for y. So we got to figure out how to get that y out of that exponent. And that's the piece, like right now, we don't know how to do, is it? We don't know how to get that y out of the exponent. So that is what we're going to work on for this second half of Chapter 5, right? We know the other part when it comes to this chapter is we want to be able to solve them algebraically. So that would be kind of like how we're starting it right now up on the board. And of course, we don't know how. The next thing is making tables and finding inverses from tables and also finding inverses from graphs, right? Those are everything you guys got quizzed on over 5.1. So same thing's still going to apply for 5.2. So I can make a table. So let's say we had some equation that was like y equals 3 to the x. And which family of functions is that guy going to belong to? What family of functions is y to the 3x going to belong to?
I don't know any families of functions.
You should know families of functions. You should know linear families, exponential families, absolute.
Exponential.
There you go, exponential family, right? And we know it's an exponential family because?
It's an exponential function.
And how do we know it's an exponential function?
Because of the x even.
Yeah. Yep, because x is in the exponent, right? So we're going to start off by making a little table. So make a table, we got our x values, and we got to plug it in to figure out what our y values are, right? So I don't know, we'll start with -2. So if I plug -2 in, I would have 3 to the -2. Uh-oh, I'm lagging again. There it goes. And if I have 3 to the negative 2, what do I do with the negative exponents? This is from semester 1. Do they change from numerator to denominator? So this would be 1 over 3 squared, which is going to give me, what's 1 over 3 squared? 1/9. Good job. Right? If I put in negative 1 for x, I would get 3 to the negative 1. And what's 3 to the negative 1? 1/3. If I plugged in 0, I would have 3 to the 0. What's 3 to the 0 power? 1. Good job. Woohoo, awesome. If I plugged in 1, I would have 3 to the first. 3 to the first is 3. If I put in 2, 3 squared would be 9, right?
What I get for trying to participate.
You're all right. Hey,
It's close.
it's called trying, right? And then we learn from our mistakes, right? Like, as soon as we figured out that that was 9, you're like, yeah, duh, I know that it's 9, right? It's not a big deal, right? We all make mistakes. You guys have seen all the mistakes I make on the board all the time when I'm trying to do problems. You're fine, right? All right. So then if I wanted to find the inverse, what do? I switch my
X and Y.
x's and y's, right? And so instead of having negative 2, I would have 1/9. And when I put in 1/9, I would get an output of negative 2, right? And if I put in 1/3, I'd get an output of negative 1. If I put in 1, I would get 0. If I put in 3, I'd get a 1. If I put in a 9, I'd get a 2. And we could try and figure out an equation off of that table, but I think that might be a little bit on the difficult side to try and come up with that equation at this part. So there's something fun that we get to do to figure out how to come up with that equation.
Can't you just do the line and then take the left, like make the y because then it's supposed to be from the line?
But if I did y, but they're not lines, they're exponential, right?
Well, that's all hard.
Right, right. So back in my day, they came up with this ancient puzzle. Did you guys get the yes, ma'am?
What I don't get is how you like determine like the numbers for x.
You can pick any value for x,
But like
right? Because, right, like, I mean, we don't, sometimes you might have a restriction, like if you had a square root or if you had x in the denominator, like it couldn't be 0, like those excluded values. But when it comes to figuring out points that would fit that equation, I don't have any restrictions on it. So I can pick any value to put in for x.
so you could have started at like 3.
Yeah, right. And if I started at 3, 3 to the third would have been 27. Okay. 3 times 3 is 9. 9 times 3 is 27, right? So you're right. So yeah. So like I kind of knew like those numbers because they're exponential. If we remember exponentials get really big really fast or get really small really fast, right? So I knew that. So I wasn't going to start off with 3 or 5 or -7 because I knew that that would either be really big or really small. So yeah. Good question. Good job. Right. So back when I was a wee little one, they came up with this ancient puzzle. So we got a couple parts to go through. They're a similar puzzle to this puzzle that's more than 2,100 years old. You remember when I said back in my day? Oh boy. All right. So anyways, mathematicians first created the puzzle in ancient India in the 2nd century BC. More recently, about 700 years ago, Muslim mathematicians created the first tables, allowing them to find answers of this type of puzzle really quickly. Tables similar to these appear in school books until recently. And there were these huge tables in the back of our books that we would have to refer to find out what these answers are. But now those tables have kind of all been put into a calculator, ultimately into a algorithm, and we usually just use our calculators when it comes to kind of solving some of these problems. So oops, maybe I can make it a little bit bigger for us. All right. So here are some examples of part of the problem. They have this log, which we're going to call a log, yeah. So like that first one, the way you would read it, and we're just got to try and see if we can figure out what's going on in the pattern, right? It would be like log base 2 of 8 equals 3. But we're just trying to figure out, if I look at these, can I come up with a pattern? All right. So let's see if we can come up with anything. Where do all these numbers come from?
I mean, I kind of get like the second one because 3 to the third would be 27.
3 to the third is 27.
Yeah. And 5 to the second is 25.
Oh.
And 10 to the fourth is 10,000. Well, the first one, and then 2 to the third is 8.
What?
Yeah. Okay.
Holy schnotzkies. I think she might be onto something here, guys. Ladies and gentlemen, boys and girls, folks. All right, let's see if that works, right? So 2 to the third, does that equal 8?
Yes, it does.
What? 3 to the third, does that equal 27?
Yes, it does.
Oh my, 5 squared, what's 5 squared? Big O 25. Look at this, 10 to the fourth. Oh my goodness. You guys see where she got all those from?
No.
No? Which one don't you see?
I don't know, I
You
wasn't paying
take the base, which is the one
Yeah.
next to the log, and then you...
She said, yeah.
That's your base, so like your big number, and then the 3 would be your exponent, and then the 3 on the second one would be your base, and then the 3 would be the exponent, and the 5 would be your base, and the 2 would be your exponent.
Yeah. 5
Okay.
squared equals 25.
Yeah.
Here. You guys see it now?
Absolutely.
That's sweet. All right. So for the next part, well, we kind of already figured out that little bit, but they gave us all of these other ones that we need to try and figure out, right? So if we pop up here for a little bit. So Medicine said 2 squared equals 3, right? Or sorry, 2 to the third equals 8. So now we got to find out our little problems down here. So what do we, like, how could we write some of that? Like a
2x equals 16.
2 to the x equals 16. And we got to figure out what our x is.
The 2 is next to the log. That's always your base number.
Yeah.
So the number that's next.
To the log is your base
Oh,
number, which is
is-
like the big number. And exponential function.
Yeah. So she took,
Oh, you were saying big number, like with an exponent. I thought you meant like big number,
like 1,000.
higher
Oh.
number.
A higher number. Nice. Yep. So Madison came up with a little pattern of, if you take that little number next to the log, that for on this one the 2, and you raise it to the third degree, you're gonna get 8. Right?
So for like the one under that, it's like, how do you know what to, wait, so it's 5.
5. And what are we gonna do to the 5? We're going to square it.
Equals 25.
Equals 25. And does 5 squared equal 25?
Wait, what'd you say?
Does 5 squared equal 25?
Yeah.
Yeah, right? So 5 squared equals 25.
That one, 10, is a big number in size. The big
Right, so
and
10.
Is
Oh.
what it's raised to.
Yep.
equals.
And you're going to raise it to the fourth. And 10 to the fourth equals.
It's just like all jumbled
So like
up.
is that all, like that's the whole point, like that's why you have to.
Oh, I think so. We're going to find out, right? So we're going to try it down here and see.
So x equals
So that's not all it?
Huh?
I hate algebra too.
It's probably just the teacher. Right. So we got to figure out what x is going to be, though. 4. 2 times 2 is... 2 times 2 is 4. Watch this. 4 times 4 is
16.
right. Check it out, right? So is 2 to the 4th 16?
Absolutely is.
All right.
Wait,
So we can even like substitute all of our little x or our question marks for x's, right?
wait, so how do you figure out x?
You're just mathematically like 2 times 2 is 4
4,
times another 2 is
8,
8 times another 2 is
12, wait,
16.
16.
So
I'm figuring out how many times.
yeah,
Yes.
right?
Wait,
So for B,
It'd be
we're going to do
x equals
2
to the what?
Oops.
power?
equals 32.
2 times 2.
so I have to figure out how many times 2 goes into 32.
Yeah.
Well, sort of. How many times do you multiply 2 by itself to get 32?
So that one's 6.
Right? 2 times 2 is
4, no, I
times 2 is
I know you're
8.
putting me on the spot.
Oh yeah, I'm making you multiply by 2s, right? 8 times 2 is
16.
16 times 2 is
Just kidding, it's 5. I said
32.
I
Yep.
said 6.
Okay, that's where I got 6 from. That's what I said.
All right?
So you're figuring out how many of like that times itself
Yeah.
to
Isn't that
get to the other number?
right? Isn't that how exponents work? Like you're multiplying it by the same guy?
Yeah, I just.
All right, so let's try C. So instead of the question mark, we're just going to make them X's, all right? I think you guys like X's better.
Why is it changing?
Because who knows what number you need to find?
That's so stupid.
It's so great. It's lovely. I love numbers, right?
So stupid. Why do they have to change it?
Yeah. So what are we going to do on this one? Same concept, but...
Let me use my brain.
So x
Yep.
squared
Uh-huh.
equals 100.
Equals 100.
See, you got it.
Yeah.
But how do I figure out what x is?
Well, on that one,
Itself equals 100.
Oh,
what would X be?
10.
10. Yeah.
You know, I'm just enjoying myself while I understand because I know it's going to get difficult.
All right, so we're going to make this guy next because now we got a nut. Oh, boy.
So 5
5.
x.
5.
To the third. Right?
No.
No?
What do we do up above?
Yeah.
Third equals x.
5 to the third.
Third equals x.
Equals
So
x.
25 times 5. Wait, am I struggling?
Wait, so now how do you figure out x?
$1.25.
Well, absolutely. That's how I do it. Yeah. Well, it's 5 to the third. So 5 to the third is 5 times 5 times 5, right?
To the $1.25.
So 5 times 5 is...
10. Wait. 25.
You guys need to help her out. 25, right? 25 times 5 is...
125.
Because 4 quarters is $1 and
Another quarter is
See, I was thinking
125.
of it like 3 quarters, and I couldn't figure out where you get the $1.25 from.
Oh
Okay, I
boy.
think I like these.
Yep, see, aren't these fun? I love logarithms. Oops, already gave me the answer out. So this guy's like a little x.
Put it into your calculator and square
Where are you going to put it into your... What?
it, right?
Put what into your calculator?
Like if we were to just like put like, we put 81 into your calculator and like square root it.
I don't know if you're square rooting it though,
Not
right?
square root.
Yeah.
That's what I'm trying to say.
No. Well, let's find out, right?
There's a way to put it in your calculator.
No.
So,
Right. So what about E? How are we going to set up E?
x
X.
4
Whoop.
equals 81.
Uh-huh.
This one's a little confusing.
Is it? No.
Why,
is it-
yeah, like you
Wait.
do the square root of 4.
It's not that before.
No, 9 times 9 is 20. Wait. 81.
Okay, it's
81 is
not
3.
Oh, right. So what's it?
9
Yeah.
times 3 is 81.
Right, because 9 times 9 is 81.
Yeah, that's what
So-
I'm trying to
So
say.
it's 3.
Oh.
Because you have to have, split your 9 into 2, and split your other 9 into 2, and then it's 3 to the 4th.
Man, look at you go, yeah. 3 times 3 is
No.
9. 3 times 3 is
No.
9. 9 times 9 is
81.
81.
Oh, I was expecting it to be little.
Right. Yeah. It's really easy, better with like 2s and 4s, right? 1 plus 1 is
2.
2 plus 2 is
4.
Yeah.
okay. Oh boy. All right, one last one. Let's throw our X in for that equal or that question mark. What are we going to do on this one?
Literally just
100.
100
X
to the X equals
10.
10.
Ooh.
Ooh.
I don't know how to do this.
This one's a little creepy.
Uh-huh.
What?
1.02.
What was it?
1.02. Right?
1.02?
One, no, I think it's just
Shouldn't
1.
it just be
2?
2?
100 squared is 10?
It's 10.
No. Right, so, right, so like on this one, let's kind of just think of it a little bit using some critical thinking skills. Like where does our X, like our X, could our X be like 4 or 5 or 2? No, because that would make it bigger, right? So we need to make it smaller.
Would it be
Like
a
a fraction
negative
or
number?
Oh, maybe a
Can it be a
fraction.
negative?
0.25.
If it's a negative, what happens to negative degrees?
I don't know.
Well, we just did a problem with some negative degrees on them. What happened here with the negative,
It's a fraction.
right? Well, it switched it from numerator to denominator, right? So it took the 3 and it flipped it down. So, whoops, I lost it. So if I take our problem that we're just working on, and if I made it negative, what? Oh, if I made it negative, it would make it where it was like 1 over 100 and something, right? Because like we had 3 to the negative 1, that was 1 over 3, right? So if we had 100 to the negative 1, it would be 1 over 100, right? So it's not quite, yep, so I would try fractions.
Okay, so
Hold on. So if we have 100 squared, so we learned about squares, or sorry, to the 1/2, we learned about how fraction exponents become radicals, right? Those are the roots.
That's what I was thinking, but I'm
Yep.
confused.
Yeah. So technically, the 1 would be here, and the 2 would be there. So what's the square root of 100? 10. Yeah.
Wait, was that right?
Yeah, that was right. So look at you. Ding, 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 ding. You got it. Whatever. You
So
did
is
it
this
too.
it?
You hit it too, Jordan. I was just waiting for them to catch up to you.
but why can't you, so like I did 80, I put in decimals 81, square root 4, I got 3.
Yeah.
So what,
Yeah.
is it just because eventually you're going to take away the 4?
Well, when you took the 4th root, you took away the 4.
Is this it?
When you took the 4th root of both
But
sides.
like, if you just get that problem,
Like this,
you have to
I
know how to
think
do the
there's
whole
more
thing,
to
because
this.
if you just get
Yeah.
log,
Because like this
whatever you
is
say, how do you say it, log what 5?
Log base.
Log base 5,
Yep.
81, and equals, and then you have 5 and 4.
Right. Because I wonder if we're going to get away from numbers and have some more equations in there. Oops.
No.
Love you guys. All right.
This is why.
This is why we love it so much,
I
right?
don't like algebra. Because, like, we learn that, and you're just like, oh, that's easy. And then you're just like,
Kabam!
wait.
Right.
It gets more difficult.
Right. Now you guys are going to Nassau. Right? All right.
Yeah.
So ultimately, they want us to kind of come up with a pattern that's always going to work on these. So those logarithms are the inverses of exponential functions. So when we want to go back and forth between exponential functions, we go to logarithms for the inverse. Or if we wanted the inverse of a logarithm, we're going to go to exponential functions, right? And so exponential functions are ways to show really big and really small numbers. So the same thing with logarithms. And in science, logarithms gets used a lot on ways to represent those really big and those really small numbers, right? All right. So we're going to come up with a little plan. Sound good?
Plans.
Yeah, I know. I gotta love plans. I wrote it all. All right. So-
Can't you just square root of x?
Turn it on.
So the, oops, can't use that color. There we go. Oh my goodness, now I can't spell. Inverses, not universes, right? So an exponential goes to a logarithm. Ready? Log a rhythm. Right? And vice versa. If I had a logarithm and I wanted to find its inverse, it would become an exponential function. Right? So if I have that y equals b to the x, we can name each one of these parts, right? We always call b the base. What do you think the x is going to be called? The exponent. In our y, because it's kind of what it equals, I just always call it the number.
I thought the base was the non-confused. I don't know. I don't know what's going on.
So when it comes to writing a logarithm, we had, for example, some log that had a base, and it had a number, and it equaled an exponent.
Well, now I get it.
See it now? Yep. So that little guy that was next to the log, what did we call that guy? We called that the base. Right? The part that it equaled, that was the exponent. And that base raised to the exponent equaled a,
The random number.
well, that number, right?
So it's basically just rearrange.
Yep, that's all you're doing is you're rearranging things. We want to do a couple more examples?
Yes.
All right. I'll think about it. All right. So let's say I gave you guys an exponential function. Give me a number. Oh, I can't do that because then I'll never be able to figure them out. Oh, we can. So let's say we had, you said 3?
Yeah.
3 raised to the
Third.
third. Well, let's keep the numbers different because I think that helps us see where everything goes. 7? Oh boy. Oops. So 3 to the 7th. What does 3 to the 7th equal?
21.
No, that's 3 times 3 times 3 times 3 times 3 times 3 times 3.
That's, no, so,
I don't know
Be
my
nice to me.
multiples.
Give me the number.
3 to the 7th.
Ooh,
2,187.
2,187. Does that work? So I can take, so is this an exponential, a linear, a quadratic, logarithm? What is it?
Just,
It's an exponential, right? Yeah. So now I'm going to take my exponential and I want to write it as a logarithm. So if I want to write it as a logarithm, what word am I going to use? Log, right?
the base is gonna be
What was my base?
7.
7 is the,
Oh, 3.
yeah, 3. Yeah. Of our number,
2,187.
2,187 equals our exponent,
7.
7.
Oh, shoot.
So you're just, so like on a test, what are we gonna get?
You would get.
Like, are we gonna get like the log or like the?
One way or the other. I can give them to you both ways. Oh, you're going to be adding these. You're going to be subtracting them, multiplying them, dividing them. These babies are going to be your friends. You are going to roll with these logarithms. Get it? Roll.
I'm so excited.
We're going to chop through them.
Why can't we just do these?
Because this is the baby step.
Because why would it be easy? Easy stuff. See, I could.
So, and then if you guys want to, you can write it all out in words, right? You have your base that you raise to an exponent that equals the number. Right? On a logarithm, you have your log with your little base of a number that equals the exponent. I know. Hey man, it's all right. So starting these off, because we do start with baby steps so that way we understand the basics of it, so then when we sit there and really spice these babies up, this part is already ingrained in your membrane.